Hi and welcome to video 7 on my series on Integration for Specialist Maths Unit 4, and in this video it's going to be quite short. I'm just going to do a couple of examples of using substitution within the definite integration realm. So you'll see example 1 is just substitution and example 2 is linear substitution, and we'll see how we go. So, or example 1, or we'll call it example A. So in A, we are integrating between pi on 2 and 0 of 3 sine x e to the cos x dx. So for my part, cos x is the u and e to the cos x is the more complicated function. So I'm going to let u equal cos x, which means that du dx is equal to negative sine x, which means that dx is equal to du over sine x, but it's negative. It looks like I've just expanded the fraction bar. Okay, now I'm going to swap out my dx. I'm also going to substitute out cos x for du, and we get something really lovely. 0, 3 sine x e to the u times by du sine x, but of course that's negative. Sine x's cancel out. Isn't that nice? And we get, I'll take the 3 out the front, or negative 3 out the front, e to the u du between pi on 2 and 0. Now we are at a bit of a crossroad here and we have to be careful of this. My two boundaries, my two terminals here are both x terminals. So we have a choice again now. You can either rearrange those into u terminals, and to do that you would just say u the upper terminal, uu2 is equal to cos of pi on 2, which is equal to 0, and the lower terminal is equal to cos of 0, which is equal to 1, and you put between 0 and 1. And that would work perfectly fine. The other option is we integrate like normal, but we don't substitute the terminals in until we've substituted u out and cos x back in, and then we substitute in the terminals, which is actually the method I commonly use and just avoid doing this and risking another mistake, so I'm going to stick with that method. But you could swap the terminals perfectly fine. So this gives me negative 3, and the integral of e to the u du is of course e to the u, how boring, between pi on 2 and 0. But I'm not going to substitute in yet because, as we said, we need to make sure we're using the right terminals. So it's e to the cos x pi on 2 and 0, and this is equal to negative 3 times e to the cos pi on 2 minus e to the cos of 0, and that's equal to negative 3 times cos of pi on 2 is 0, so it's e to the 0 minus e to the 1, and that's negative 3, 1 minus e, and we can just make that we expand the negative m, and we get 3e minus 3 as our definite integral. So that's question A, and the only new thing really there is the recognition that we either have to change the terminals to be u terminals and substitute them in at this stage when we have e to the u, or don't change the terminals but make sure we've substituted our u back out before we substitute the terminals in. Very important concept. And we'll have a look at question B. So I'll just drag it over here. And in example B, oh, disappeared. Okay, there we go. In example B, we've got the integral of between 2 and 0 of 3x squared square root of x plus 2. So I might do this the other way, and this is a linear substitution because our square root is a complex function, but it's hard to do when we've got an x plus 2 in there. So what I'm going to do is I'm going to let u equal x plus 2, which means that du dx equals 1, and dx therefore equals du. Now if u equals x plus 2, then the upper terminal, u upper terminal, is equal to 2 plus 2, which equals 4, and u lower terminal is equal to 2 plus 0, which equals 2. And so we now get the integral between 4 and 2 of 3x squared, sorry, my apologies, we swap out the x, 3x plus 2 squared times the square root of, no, hold on, let's put the square root of u here, and let's recognize that if u equals x plus 2, then x equals u minus 2. 3u minus 2 squared, that's better, and the x can be swapped directly for du, so we get du there, and I've swapped the terminals. So I'm going to work out my definite integration and never have to look at that pesky x again. And this is equal to 4 and 2. Now the u is better, but I have this quadratic I've got to deal with, so I'm going to have to deal with that. I get 3 times u squared minus 4u plus 4 times by u to the power of a half du. And this is the integral between 4 and 2. I'll take the 3 out the front, and I get u to the power of 5 over 2 minus 4u to the power of 3 over 2 plus 4u to the power of a half du, which is equal to the integral between 4 and 2 of u to the power of 7 over 2 over 7 over 2 minus 4u to the power of 5 over 2 over 5 over 2 plus 4u to the power of a half over, sorry, not a half, 3 over 2 over 3 over 2, and I've done the integral now, so I don't need that anymore. It's a square bracket between 4 and 2. Now I'm going to simplify this before I do any substitution. This gives me 2u to the power of 7 over 2 over 7 minus 8u to the power of 5 over 2 over 5 minus 8u to the power of 3 over 2 over 3 between 4 and 2. Now see, 4 is going to be nice, 2 not so much. So this will give me 3 brackets. I'll use the double brackets. 2 times 4 to 7 over 2 over 7 minus 8 times 4, 5 over 2 over 5 minus 8 times 4, 3 over 2 over 3 minus 2 times 2 to the power of 7 over 2 over 7 minus 8 times 2, 5 over 2 over 5 minus, oh, I've changed that plus into a minus, that should be a plus, so that's a plus 8, 2, very common mistake that, by the way, so just be careful. There we go there, and I'll just put this in my calculator to get an exact value answer. And that simplifies down to 704 over 35 minus 128 root 2 over 35, which is approximately equal to 14.9423. I hope. I've just done that in the scientific calculator. It's fairly intensive, so you just got to be careful that you're getting the right answer out of these as well. So there's a second example, B, and here's the work that you should be doing. 11D and 11E is now covered, so make sure you ask questions as you need to. All the best.